Welcome. My name is Matt Yankowitz, and today my group and I will be giving you a flavor of the work that we do here. The Yankowitz Lab is an experimental condensed matter physics lab based in the Physics and Material Science and Engineering departments at the University of Washington. We specialize in the investigation and control of novel electronic states and quantum materials, primarily focused on two-dimensional van der Waals materials such as graphene. We study these materials at low temperatures and in high magnetic fields, where the unusual effects of quantum mechanics become the dominant force driving the behavior of our devices. Our goal is to use a combination of our novel device fabrication with 2D materials and our electrical and microscopy characterization techniques to discover and control exotic new quantum phases of matter. Eventually, we hope to utilize these properties to develop next-generation quantum technologies. In the following few minutes, some of the members of our research team will give you an overview of how we fabricate and characterize devices made of two-dimensional materials, as well as the other experimental capabilities of our lab.
We typically begin our device fabrication by isolating two-dimensional materials from bulk crystals through a mechanical exfoliation process. Van der Waals materials have a strong in-plane bonds but have stacked layers of the 2D sheets that are held together by a weak van der Waals interaction. We utilize the Scotch tape exfoliation technique, demonstrated here, to thin down the bulk crystals to the atomic limit onto a silicon wafer substrate. Here, we are isolating the bulk graphite into graphene, a honeycomb sheet of the carbon that is just 1 atom thick. Materials like graphene do fine out in the open, and we can exfoliate them here in our lab. However, many other van der Waals materials degrade or evaporate in open air, including many of the 2D magnets we studied. For this, we utilize the shared fabrication facilities with the glow boxes filled with the inert gas in order to keep our materials pristine.
The two-dimensional nature of these materials allows us to stack individual layers together to form heterostructures with new and exciting properties. With our van der Waals transfer station, we can precisely stack different atomically thin materials with micrometer precision. To do so, we utilize sensitive micromanipulators to control a microscope slide within a fixed sticky polymer to carefully peel exfoliated flakes off their silicon substrates. We repeat this process layer by layer until we assemble the desired van der Waals heterostructure. Sometimes, even precise rotational control between neighboring crystals in the stack can manifest exciting new electronic phases of matter, including superconductivity, ferromagnetism, and other strongly correlated electronic states. Our transfer setup enables us to control the twist angle between crystals to better than a few hundredths of a degree.
Once the desired heterostructure is created, we proceed with a series of nanofabrication processing steps in order to transform it into a device that we can measure. To do this, we make frequent use of our optical microscope in order to see our device, which often has features that are only around a micrometer in size. That is about 1/100th the width of a typical human hair. We also frequently utilize our fume hood for chemical processing and for spin coating various polymers onto our silicon device substrates. We further process our samples in various shared fabrication spaces, either in neighboring labs in the physics building or utilizing a world-class cleanroom in the Washington Nanofabrication Facility. We use procedures including plasma etching, electron beam lithography, and metal evaporation in order to modify our assembled stack of van der Waals flakes into a functional electronic device.
To prepare our devices for measurement, we often need to do basic electronics work such as wire bonding and soldering. Once our devices are completed, we utilize our room temperature probe station to do some simple electrical measurements to ensure that everything is working properly. We characterize our devices here using a combination of sensitive voltage suppliers and locking amplifiers. This gives us our first glimpse of how our device is behaving before we cool it down to low temperatures where much of the interesting physics emerges.
Once the device is ready, we can characterize our samples at ultra-low temperatures in high magnetic fields and sometimes at extremely high pressures. The room you see here is the second lab space in the Yankowitz Lab and will be the site for a low-temperature scanning tunnel microscope that is expected to arrive very soon. Our scanning tunnel microscope is cooled by liquid helium and will operate at about 4.5 Kelvin, just a few degrees above absolute zero. It will also have a 5 Tesla magnet, which is about 1,000 times stronger than your typical fridge magnet at home. The scanning tunnel microscope that will soon leave here will allow us to image the structural and electronic properties of our devices with atomic resolution, yielding important insights into the microscopic properties of our samples.
In addition to our scanning tunneling microscope, we are also expecting the arrival of a low-temperature cryostat in the near future. This system, which will be located where I'm currently standing in our lab, will have cryogen-free refrigeration, allowing us to characterize our devices from room temperature down to 1.5 Kelvin, as well as a large 12 Tesla magnet. Additionally, we frequently make use of other fridges already on campus, which allow us to measure our devices to even lower temperatures of 10 millikelvin, just a tenth of a degree above absolute zero. There's a lot of exciting work to be done in these two-dimensional quantum systems, with significant application potential for the next generation of quantum electronic devices. Stay tuned for more exciting things to come from our lab, and feel free to contact any of us if you have questions about our work here. Thanks for watching.